So far we have been talking about the question of photons, but without reference to the wavelength, the color of the corresponding light. Of course, we are interested in building color cameras, colors that can also capture not just the intensity but also the color of the objects surrounding us. And there are three basic techniques by which you can build a color camera. The first would be a prism. And that could be done with two very well aligned cameras. So notice that these silicon-based cameras, be it CMOS or CCD, by themselves they are actually colorblind. They just collect photons. They couldn't care less about the corresponding wavelength. So we have to do something special to make them color sensitive. And one is to divide the spectrum into different parts and to send photons coming from different parts of the spectrum to three different wavelengths, for red, green and blue, with a prism. A second technique is with filter mosaics. There we can use many different subdivisions of the spectrum. It doesn't have to be three, it doesn't have to be red, green and blue. But usually, of course, it will be, and we will see it's a special arrangement. And then finally, the filter wheel, with again the same comment. You could now have different filters put in front of the camera. Okay, first of all, the prism. So what happens here is light comes in from the left, hits the lens, then light goes on and is being, with a prism, divided into three parts of the spectrum. So let's say the blue part goes to the sensor on top, the green part goes to the sensor on the right, and the red part is being sent to the sensor at the bottom. These are three equal sensors. They themselves do not capture anything color related, but we make sure that with the prism, light coming from different parts of the spectrum are sent to the three different sensors. And here you see that operation a bit in detail. So that the prism, well, we have heard about Newton and all that. So shining light onto the prism, white light, splits the light into the different parts. And here you see such a prism that is built into a camera. And the incoming light is split up in the three different parts. So if you look through the prism again, you see how every part of the prism has now indeed only coming light from a certain part of the spectrum coming through. So that's one expensive way of generating color images. It has one big advantage, namely that you have the full resolution of each of the three cameras being used. A second type of camera that can capture color is based on filter mosaics. And these are polymers baked on top of different pixels. So you would have like a polymer that lets through blue, red or green light. So here on the left, the different squares are different pixels. And you see some of the pixels have on top of them a red filter, some of them a green, and some of them a blue filter. In fact, you only have all the colors for every 2x2 patch. And that means you in fact lose spatial resolution. You don't have at every pixel and red and green and blue. You only have one color per pixel. So it exchanged a bit of spatial resolution, effective spatial resolution for spectral resolution if you want. That's different from the previous case, because there you would have for every pixel of the three identical sensors, you would have red and green and blue. So their spatial resolution was kept to the full, at the expense of having 3 very precisely aligned sensors, because they have to be precisely aligned. This is a much simpler setup. No 3 sensors, only 1. But as said, you lose spatial resolution. On the right hand side you see a real chip with real polymers on top, as described on the left. By the way, this particular layout where you have red, blue and then twice green in one 2x2 block of pixels is called the bar filter layout. You have twice the green part of the spectrum because that's also the part of the spectrum people are most sensitive to. So maximal sensitivity of human perception is about 555 nanometers. Okay. Now, usually this type of camera is used in conjunction with so-called demosaicing software. Software that tries to imagine a red, a green and a blue readout for every single pixel. And as you can see, you don't have that. You have to infer it. It has to be calculated. It has to be estimated. And that's what this demosaicing software does. Because indeed, if you would have that kind of input in this image by that type of sensor, what you actually get is this kind of somewhat decolored output because of that lack of spatial resolution for all 3 channels. So the mosaicing will turn this into that kind of image again. Again, you see, if you look at the raw outcome of those sensors, you see all the decoloration, especially near the borders. You have to compensate for that. And then finally, the third way of getting at color is with a filter wheel. So here we have this wheel here in the black box with different filters, and you can shift one after the other in front of the camera, and every time take an image. So you have the full resolution of the camera, and you have maybe now far more than just 3 parts of the spectrum, but you see, this is of course a lab situation. This is a lab setup. You can't do that for a real camera in a mobile phone. And it will take time, because you have to shift one after the other filter in front of the camera. So that makes it only useful for static scenes as well. So in summary, going through the 3 possible ways of getting colored images. You have a prism. That's only good for high-end cameras, because now we have 3 sensors rather than 1. And you have this complicated prism setup and everything. The 3 sensors have to be very well aligned to make sure that information coming from the same point in the scene is also hitting corresponding pixels in the 3 sensors. But anyway, you have 3 sensors, resolution is high, the full resolution of those sensors. The cost is also high. The frame rate can be high because everything happens at the same time. Fewer artifacts because it's really capturing all parts of the spectrum, the 3 parts of the spectrum in this case, for every pixel. And there are typically 3 bands. Then the mosaic. Okay, in this case only 1 sensor, but at the expense of resolution, because you have red, green and blue at different pixels. You have to do special software trying to imagine again what the full spectral information would have been. So the resolution is only so. You lose resolution if you don't do anything special and you work per 2x2 patch as a single pixel. Okay, the cost is low. Only 1 sensor. That's the vast majority of cameras, by the way. Frame rate can be high, normal acquisition time of a single sensor. Artifacts, well, there will be some aliasing near the borders, as we have seen. 3 bands. And then finally, that filter wheel, well, there's only one sensor, so we have good spatial resolution as high as the sensor's resolution would be. You have an average cost, not so expensive maybe, but the frame rate is very low. You have to turn that wheel, take image after image. That isn't good. If there's motion in the scene, that is bad news. That will give you some blur. However fast you rotate that filter wheel. And you can have 3, but also more spectral bands in that case. Anyway, dominant technology, middle column. Okay, so that's about the sensors themselves. But now we have to say a bit more about how the geometry behind image acquisition actually works. Actually, artists have been after the rules of perspective projection, because that is what this will turn out to be, for a long time. Okay, so here we are again with the pinhole camera model. We have the object in the outside world. We have the center of our lens, where all these rays, these straight rays, go through to project onto the light sensitive plane at the back of the camera. So the pyramid on the right will give rise to this image on the left. And you see through the way this pinhole projection works that you have a reversal. So here we have a pyramid on its head. Now what people often do in order to avoid all these sign changes in the way of projection is to have this virtual image plane in front of the camera rather than inside the camera. And there, this pyramid, this virtual pyramid, is the same size as that of the image, but everything is also still in the right direction, so you have no reversals, no sign changes there. So most of our analysis will do as if you have this virtual image plane in front. So, first of all, the center of the lens is the center of projection. So we can summarize projection as a straight line starting from a point in the scene, running through that center of projection and hitting the back of the camera, the light sensitive area. And all these rays of projection run through the same point, the center of the lens, which is that center of projection. Notice the virtual image plane we have, just mentioned that. That's just for ease of calculation. And this entire model, this pinhole model, that amounts to what we call perspective projection. So it will lead to all these effects of things that are actually parallel in the world, may seem to intersect in the image. Things getting smaller as they move away from the camera, and so on. Okay. So revisiting our original drawing, we'll now focus on this part. What actually is this image projection like? So what's happening in that image plane? We want to build a mathematical model formulating the whole image formation process. So, suppose you have again object here on the right. We have a point on that object. We call it here x, c, y, c, z, c with its three-dimensional coordinates. These three-dimensional coordinates are expressed in a world coordinate system, indicated with the red axis. The center of projection corresponds to the origin of this world coordinate system, or in other words, we have actually fixed the world coordinate system to the center of projection, so that its origin lies at the center of projection. And that's not all. We have also chosen the world coordinate system here, so that the z-axis corresponds to the optical axis. So it's an axis orthogonal typically to the image plane. xc is parallel to the rows of our camera, the pixels in our camera, and yc follows the columns, is parallel to the columns of our camera. In the camera plane itself, that image plane that you see there as a parallelogram, we are counting in terms of pixels, horizontally and vertically. U and V are following the rows and the columns of pixels in that image plane. Okay, so the origin lies at the center of projection in this particular choice, and we will later generalize it. The z-axis coincides with the optical axis, and the x-axis is parallel to the image rows, while the y-axis is parallel to the columns. So what happens in terms of image projection in this particular case? So here we are for the two coordinates in the image plane. The coordinate u in the image plane is found as f times capital X over z. Or in other words, u stands, the ratio of u over f is the same as x over z. Follows from equal triangles, as you can see from that image. Notice that f is actually the distance between the image plane and the xy plane in front here. And the same for v. So that vertical orientation in the image plane, the coordinate there is following this equation. Again, equal triangles. So very simple projection equations. But that's also a very simple setup. We have, in this case, a very particular choice for the world coordinate system. Notice that simple as the equations may be, we could even get to simpler equations. Namely, if all the points are at the same distance from the camera, so z is a constant, then of course f over z would be a constant as well. In that case, the image, the uv coordinates, are just a scaled version of the xy coordinates in the world. So if z is constant, that means all the points are actually now lying in a plane orthogonal to the optical axis, so parallel to the camera. Then the projection amounts to a scaling with f over z. This model, where you have this kind of scaling going on, can be used under slightly more general conditions as well, but then it becomes an approximation. So you could say, if an image is not too, if an object is not too deep compared to distance to the camera, so the variation in z is rather small compared to the z, the distance to the camera, then this approximation holds by a good degree. So if you have quite undeep objects at a sufficient distance from the camera, the same kind of scaling equations work well. We call that orthographic projection, or pseudo-orthographic projection actually, because you also have that scaling. So it's like orthogonal projection onto the image plane and then the scaling. So it's a bit simpler than perspective projection. And again, for objects far enough from the camera, so that they become quite deep compared to their distance to the camera, that may be a good approximation as well. Here you see an example on the left-hand side, if you have a cube, the cube is far enough or small enough, this is the kind of image you would get. Things that are parallel in the real world, still kind of parallel in the image. If you come too close with your camera though, or the object is too big, and the depth variation is too big, you have to go for full perspective to be precise enough, and that gives you that kind of perspective image, where things that are actually parallel don't appear parallel in your image any longer. So the perspective projection model is by itself also not really the complete storyline. As we have seen thus far, because the 3 coordinates are specified in a world coordinate frame that is more general. So far we have said, okay, let the world coordinate axis be somehow linked to the camera. The origins are the center of projection, the rays or the x and the y coordinates are parallel with rows and columns. We have the z-axis parallel with the optical axis and so on. In general, you have a camera standing here, the world coordinate system you want to use in your application is completely independent. So that's something we have to free our calculations from, this particular assumption of this very particular choice of world coordinate system. Secondly, we are not calculating our position in the image plane in metric terms. We are calculating in terms of pixels. How many pixels to the right, how many pixels down. So we have to express the coordinates not in metric terms, but in terms of pixel rows and pixel columns. So these are 2 necessary generalizations. We'll go through them now. In fact, that's not even a complete story, because we would have to then also consider radial distortion and all those other things. But that we won't do now. Okay, for these 2 generalizations in red. So again, we have a camera. C there is a center of projection. And then again, we have the world coordinate axis in red, and now we see these 2 are decoupled. The camera's origin, or camera center of projection, is no longer at the world coordinate origin. And the axes of the world coordinates are no longer aligned with the main directions in the camera. We have those main directions in the camera being R1, R2, and R3. R3 being the optical axis, so orthogonal to the image plane. And R1, R2 corresponding to the rows and columns. We had the equations for projection before, we can just generalize them. So we had U is F, capital X over Z. But now we have to generalize those. X is now the projection of the vector P minus C. So P is a point in the world there, the red point on top of the slide. C, the center of the camera. So we have P minus C. We project that vector with an inner product. That's what the brackets stand for. Inner product with R1. That gives us X. Same for Z, same for Y. Projection onto R3 for Z, projection onto R2 for Y. So on the right hand side, with these inner products of P minus C onto R1, R2 and R3, we have the same projection equations that we had before, but now written for these more general conditions. Okay, so if you start to elaborate the equations, that is what you get. It looks kind of ugly, but it's just what we have been talking about before. So for P, we have the coordinates x, y, z. For C, we have coordinates written here, C1, C2, C3, in the world coordinate axis, the red axis. So you have them here, right? X, Y, Z for P, and C1, C2, and C3 for C. So that's P minus C inner product with respect to R1 for the numerator of the first equation. So you have the multiplication with the three components of R1, R11, R2, R13. And then the same for all the other expressions, similar inner products. And that gives us U and V. So we have still now a projection onto the image plane in metric coordinates, UV. So this is the first step in our generalization. How do the projection equations look like if we decouple the world coordinate axis from the camera? But we had a second generalization as well, and that was when we would go from metric coordinates in the image plane to pixel coordinates. So rows and columns of pixels. And that's what the second step is about. We are not very interested in U and V, these metric coordinates that we just had from the previous slide. We want to turn these coordinates into these pixel row and pixel column coordinates. And that is what these two equations on top here do. We go from U and V to X and Y. And X and Y are pixel coordinates. And we see that these transition equations, kxu plus sv plus x0, and y is ky v plus y0, do exactly that. Kx would be like the number, the horizontal size of the pixels in metric terms. So how many pixels you have per unit length horizontally. Ky does the same, but now vertically. X0, Y0 are the position of the intersection of the optical axis with the image plane. So if you have this optical axis, it will typically shoot almost through the middle of that image plane. Typical position, not quite the middle, but about. But that's not from where we start to count our pixels. Typically, if we build up an image, we start to count from a corner, like in this case, the top left corner. We start to count columns from there. And say, for the rows, we start on top and go to the bottom. So x0, y0 is a shift that we apply. And that's where the optical axis intersects the image plane. So we shift to the top left. And then you have S. And S is so-called skew. The skew gives the indication of how non-rectangular the pixels are. So typically the rows and the columns for the different pixels will be orthogonal to each other. But it can be that for practical reasons, if you want to be very precise, you have to handle them as not perfectly orthogonal. And that can, for instance, be the case because the sensor is not perfectly parallel to the lens. There may be a little bit of an angle, and that gives this skew between rows and columns. So typically, S will be 0, no skew, but it may differ from 0, if there is one. So in that way, we go from these metrical to pixel coordinates. So now we have these two generalizations, and both have to be applied. Some notes. So U and V in general will just be some real numbers. So also will be X and Y. But of course, often we are only interested in integers for the pixel coordinates. So you may have to round off. 2, this horizontal size of pixels over vertical size of pixels. That's called the aspect ratio. So an aspect ratio of 1 means you have a square pixel. The width and the height are the same. The parameters in these equations are the so-called internal camera parameters. So kx, ky, s, xo, yo. When these parameters are all known, we say that our camera has been internally calibrated. On the previous slide, that generalization would involve a new center of projection C, but also these orientations R1, R2, R3. Now these three vectors, R1, R2, R3, together build a rotation matrix. They are all orthogonal. They together build this 3x3 matrix that indicates the orientation of the camera with respect to the world coordinate system. We call C and R the external camera parameters. And if they are known, we say that the camera has been externally calibrated. When all parameters are known, so those in these equations, plus C plus R, the rotation matrix, we say the camera has been fully calibrated. So a fully calibrated camera is a camera of which we know the position in space, where it is, how it's oriented with respect to the world coordinate system of that space, plus we know all the settings of the camera. Now finally, we want to simplify a bit the expressions of projection. And for that we will use a trick. We will use so-called homogeneous coordinates. So on top, on the left you have the coordinates x and y, but we extend them with this third coordinate z. And the way we interpret that triple in Cartesian terms is that's the same as the pixel x over z, y over z. Same for 3D. So if you have 3D coordinates x, y, z, you can extend them with a fourth one, w, and they say the way to interpret this thing is at this point in space. Now, we will use these so-called homogeneous coordinates on the left as a way of linearizing our equations, because unfortunately you have some linear aspects in the different equations that we saw thus far. It was pretty clear the first time, so if we go back now, this first generalization, clearly non-linear, because you have this ratio, obviously non-linear, right? So we will linearize this equation with homogeneous coordinates. And then the second generalization that we also saw, where we went from the metric coordinates to pixel coordinates, namely these ones, again non-linear, because of the translation, the addition at the ends, that makes the thing non-linear. And again, also those equations will be linearized by the use of homogeneous coordinates. These guys. Notice that homogeneous coordinates are also only defined up to a factor. If I multiply these homogeneous coordinates with some non-zero factor, their meaning is exactly the same point. Because if I make those divisions on the right, the factor will drop out, will cancel. So here we go again. We have the first equation, the first generalization to a world coordinate system now completely decoupled from the camera, blatantly non-linear, and we can linearize in this fashion. So we have a matrix multiplied with this vector here, and that gives us these homogeneous coordinates up to a factor, as we just saw. So we have this down here to indicate that. So this is all defined, but only up to a non-zero factor. Now, the equations at the bottom of the screen are actually identical to the equations on top. So if you see, if you multiply the first row of this matrix with this vector here, and you do the same for the second row multiplied by that vector, and then you divide by the third row multiplied with the vector, you have exactly that. So, by interpreting the result of this matrix multiplication, so purely linear multiplication, it's all linear now, we get these homogeneous coordinates. And homogeneous coordinates make sure that we have this interpretation above. The ratio, actually, is your underlying interpretation. But at the level of homogeneous coordinates, this is all linear. Now we can go a bit further. And also involve the second generalization. So we had the equations on top. But we can also rewrite those equations as this set of equations below. And again, we have to interpret these as homogeneous coordinates that result. Notice here we are, in fact, dragging in the translation over x0, y0 with this multiplication. But again, the result, nicely linear. Matrix multiplication. And then it's a matter of combining everything. So we had the linearization on top for the first generalization. We had the linearization below for the second generalization. And we can combine them. Because the first leads to the vector that we have here. And that gives us the vector on the left. So we concatenate the whole matrix operation. And we get the thing on top. That's the concatenation. So now we have one linearized version going from the vector that we called P minus C before, directly to these pixel coordinates on the left, but in homogeneous terms. By the way, we can change a little bit the equations on top, but those equations on the bottom, at the bottom, we in fact peel out the f values from that matrix that we have on top, and that gives us the product of these two matrices. And that cleans up the thing, because now we have this rotation matrix again, the orientation of the camera. That's a rotation matrix. Here we have f. F actually is more an internal setting of the camera, right? So we can take that together with these internal parameters. So we have internal parameters here. F is also kind of an internal parameter. We will combine these two, and we call that the product of these two matrices, the calibration matrix of our camera. So that's the calibration matrix. Okay, we are almost there. That now results in this very compact description, going back. So, on the left there, the first two matrices, that's K, and then we have the rotation matrix R, and then we have P minus C, okay? That is giving the result on the left. And that's what we have here as well. So, if you look at the 2D coordinates on the image plane, pixel coordinates, they'll call K, I'll transpose P minus C. So we have the calibration matrix and the rotation matrix times P minus C. So this is now a very linearized version of the perspective projection that we have been describing thus far. There's one more step we can do. So, as you see, this, in fact, still this translation. So, if you go from capital P to lowercase p, you still this translation minus c going on. And that's a non-linear part as well. Again, homogeneous coordinates can be called to the rescue, and we can now go to p tilde there on the top right. These are homogeneous coordinates for the three-dimensional point, and we'll start to use those and linearize the remaining nonlinear bit, the minus C bit. And that's what we get. So, what this represents is the transposal rotation matrix, and then minus R transpose C, which is a column. So we have 3 columns coming from R transpose here, and this additional column. So this is a 3 by 4 matrix. The bar just means 3 columns here and 1 remaining column coming from here. So this is a 3 by 4 matrix. Or in net terms, we are going here fully linearly with a 3 by 4 matrix. Well, we have to multiply by k, but it's 3 by 3. So the entire thing is a 3 by 4 matrix, yielding the image coordinates p, lowercase p, directly from the world coordinates p tilde, homogeneous coordinates, both in 3D space and in the image. So, mathematically, you could say that perspective image projection at the level of homogeneous coordinates in 3D and 2D amounts to a 3 by 4 matrix. So we have a pure matrix multiplication here applied to the coordinates in 3D to get at the image coordinates in 2D, but in homogeneous terms. So that's a 4 vector and that's a 3 vector. And again, the whole thing is only defined up to a non-zero scalar homogeneous coordinates. So, if you write K R transpose as M, we have something like that. We have M, the 3 by 3 matrix, and then T, the column coming from the minus R transpose TC part multiplied by K. So that gives you that. M is rank 3. So M is 3 by 3, T is this 3 vector, column vector, so this is 3 by 4. Okay, this is about the geometric model of the camera. So how the geometry of image formation works. But of course we also have to worry about what is the intensity reaching a camera. And that's the photometric bit. We don't want to dwell on that, but one should of course not underestimate how complicated you can make this. And in principle, people are often not only interested in the geometry of image formation, but also in how exact intensities of the image come about. We won't deal too much with this though. So here a shortened story. So we can model the whole process actually as 2 bits composed. First of all, you go from the object radiance, that's the amount of light being sent to the camera from an object. So reflected light, light reflected by the object towards the camera. And translate that into image irradiance, how much the camera really gets from that. And then you can go from that image irradiance to the pixel gray level, what the camera makes out of the incoming intensity. So we will make a number of assumptions. And the question is, as the first part, how does that radiance, that light reflected towards the camera, translate into irradiance, what the camera really captures in terms of incoming intensity? That's the first thing we will look at. And here we have a drawing. So we have the object, there's a patch there that reflects light through a lens in the middle, back onto our camera. Of course, we have a limited diaphragm in front of the lens and so on and so forth. Now, we don't want to dwell on how to make these calculations. Just to summarize the results. So in general, if you look at a certain lens area, AL, so I said depending on the diaphragm, the opening, you get more or less. So let's say the part of the lens not covered by the diaphragm would be AL, the area. Then the focal length, which is, as usual, the distance between the lens and the image plane. Then we have the radiance, so how much, in fact, is being reflected towards the camera by the object. The important thing is this cosine to the power 4 of alpha. And alpha is the angle between the optical axis and the direction of incoming light. We call that the cosine 4 law. And what it actually says is that there is a very sharp drop off of how bright a patch will look like depending on how oblique the angle alpha is. If you have a head-on view, it may still be pretty bright. But the more it's at the corner of our eye, so to speak, the corner of the camera's eye, the darker it gets. And there's a drop off that is pretty steep, cosine to the power 4 of alpha. You have to imagine how quickly that goes down. And that is something that is true in general. So near the border of the image, things get darker. So in the center you have a higher intensity than near the edges. Here you see an example, a bit exaggerated, but especially if you have wide-angle lenses where incoming rays can be quite oblique, you have a strong cosine 4 effect. So you see this drop off of intensity here, maybe even clear here in the bottom, where you have this kind of mosaic, the camera panning from left to right also. You see, in any case, you see these darkening corners. They are all pretty wide-angle cameras. So it's people also very easily gloss over this perceptually. Our eyes accommodate for those differences pretty easily. But if you start to objectively measure intensity, the effect is very much there. So you have a darkening effect towards the rims of your images. That is the first effect. That's how much light does the camera get in? And then that incoming signal has to be turned into this electric signal that the camera makes. And here is kind of the equation of what that happens. So if the irradiance I, which is already subjective to the cosine 4 law, as we just saw, if you have that coming in, what the actual signal F will be is this composition. So it's not just I, it's not passing on something just linear of I is raised to a power gamma, the gamma factor of the camera, then multiplied, and then you have plus D. Now D is what you get even if I is 0, if you notice. So that's kind of a noise level. You always get some signal, even if the cap would be on your camera, you still get the signal. D, that's noise, that's just thermal noise. It's an illusion to think that will be a signal. But it means there will be noise on top of your signal. Then gamma is a certain non-linearity, as you can also see. Now fortunately, for CMOS cameras, we are very close to 1. For CMOS camera, we have a gamma close to 0.9. But for CCD cameras, one was closer to like 0.6. So CMOS camera, CCD cameras are pretty non-linear. CMOS cameras are behaving a lot more linearly in that equation. And G finally is the gain. You can control that with the diaphragm of your camera. By the way, D is also temperature dependent. If temperatures get higher, images get also noisier. So D will increase. So we have D, which is a dark reference, for reasons I mentioned before. Even if the camera is completely shielded off, there will be some signal in complete darkness, D. Then we have the gamma factor and then the gain. The gain controlled by the diaphragm, depending on how much light you let in. And gamma, not so much in the past, but nowadays with the dominance of CMOS cameras, more and more indeed close to 1. So we get closer to this pure linear dependency of irradiance and camera signal. So that ends this part, and then from now on, in the coming lectures, we will actually start to use these images and make sense of them.